Hey everyone, in this video we're going to work through question 2 from the 2025 USNCO second round. So this problem focuses on solubility equilibrium and acid-base chemistry. So I'm going to explain this step by step and explain not just the calculations but also the chemistry behind them. So let's start. Okay, and the first question, we just need to draw a Lewis structure for oxalate ion. I think will be easy for you, and let me explain. So there are two carbons atoms connected by a single bond in the middle. Let me show you this. Something like this. Okay, and each carbon is attached to two oxygen atoms, one with a double bond and one with a single bond. So the two oxygens with the double bonds have two lone pairs. And the oxygens with the single bonds have three lone pairs and each carry the negative charge. So something like this. Negative. And here also, this oxygen atom is also negative. So the total charge, as you can see, is -2 because there are two negative oxygens. Okay, and there is also resonance. You can see, you can do something like this. Okay, now this oxygen atom becomes negative. Something like this happens. And this is called resonance. Also, could be like a few different resonance. So let me show you. But in the real chemistry, in the laboratory, you will see that some chemists doing like this. So the negative charge is just located between two oxygen atoms. And in the real life, all carbon-oxygen bonds are the same length. Something like this. So this and this is just a negative charge. So it's just located between two oxygen atoms. And as I said before, in the real life, all carbon-oxygen bonds are the same. So okay, now I think we can move to the next question. So now the second question, and here we are asked to find the molar solubility of calcium oxalate in pure water. So, and first of all, let's clarify what is molar solubility. So molar solubility is the maximum number of moles of a solid that can dissolve in 1 liter of water. In 1 liter of water before the solution becomes saturated. And our goal is to find how many moles of oxalate, calcium oxalate can dissolve per liter of water at equilibrium. Okay, so calcium oxalate is a soluble salt, which means it doesn't fully dissolve in the water. And instead establish the equilibrium between the solid and its dissolved ions. So now we're gonna write the reaction. This is solid, dissociates calcium 2 plus and oxalate ion 2 minus. Okay, let me clean this. Okay, and this equation tells us that solid calcium oxalate dissociates into the calcium ions and oxalate ions in solution. Okay, and here we see that calcium oxalate, as I said before, it's a solid. And pure solids, they are not included in the equilibrium expressions, including the solubility product constant as a KSP, right? So the reason is that the activity of pure solid is a constant and defines as a 1. So it's just equal to 1. So the actual constant, equilibrium constant, look like this. Calcium 2 plus, oxalate ion over the concentration of calcium oxalate. But since the activity of calcium oxalate is just equal to 1, we're just writing that KSP will be just equal to the concentration of calcium 2 plus, calcium ions multiplying by the oxalate ions. And therefore, calcium oxalate doesn't just appear in the KSP expression. So now the solubility product expression depends only on the ions in the solution. Okay, and now let's define the molar solubility. So let, for example, X be the molar solubility of calcium oxalate, right? I mean the calcium oxalate, my bad. So our X is just the molar solubility of calcium oxalate measured into the moles per liter, which is just equal to molarity, right? So that means that we have some X moles of calcium oxalate dissolved per liter of water. Okay, and from the dissociation equation, this expression, let me clean this. Okay, and from the reaction, we can see that 1 mole of calcium oxalate produces 1 mole of calcium 2 plus ions and 1 mole of oxalate ions. So therefore, if we had some X moles of calcium 2, I mean the calcium oxalate, the concentration of both ions will be just equal to also 2X. Okay, and the concentration of 2 ions, they will be they equal, and they just equal to X. Okay, now we're just substituting this into the expression KSP equation. So KSP will be just equal to X multiplying by X, which is equal to X squared. And now we are given the solubility product constant, which is equal to 2.7 times 10 to the power of negative 9. And our X from here is just equal to square root of KSP. If we do this, our X will be just equal to 5.2 times 10 to the power of negative 5 molarity. Okay, and this number represents the molar solubility of calcium oxalate. So in other words, only this amount of moles of calcium oxalate can dissolve in 1 liter of water, and any additional calcium oxalate added to the system will be just the remain as a solid. So only this number will be can dissolve in the water. And if you want to like add some more calcium oxalate into the water, for example, some more, I don't know, like 1 mole, this 1 mole will be just remain as a solid. And because the value of KSP is extremely small, calcium oxalate is only very slightly soluble in the water. Okay, and now we're moving to the next question. Quick note, if you want to seriously deepen your understanding of chemistry, check out my website, chempra.academy. There you will find full chemistry courses, challenging practice problems, free resources, my original Olympiad-style questions, and detailed chemistry blog. Everything is organized in one place for students preparing for competitions or advanced exams. Alright, now let's continue. Okay, now in this part, we will calculate the molar solubility of calcium oxalate in a 0.100 molarity of calcium chloride solution. So before doing any calculations, I will explain to you what is the difference compared to part B. So in part B, our calcium oxalate was dissolving in just pure water. So we had some pure water and we had our calcium oxalate, which was dissolved in this container, right? But now in the part C, the solution already contains the calcium ions because calcium chloride will dissociate in the water. So something like this happens in the solution. I mean, this 2 plus 2 chloride minus. So now in our solution, in our container, we have, of course, water and the concentration of calcium ions. And our the calcium oxalate will put our calcium oxalate into this container with the H2O and the concentrations of the calcium ions. So let me clean this. Okay, so calcium chloride is a strong electrolyte, so it will dissociate completely in the water, like this. And that means if the initial concentration of the calcium ions was 0.100 molarity, the concentration of calcium 2 plus will be just equal to the same, 0.100 molarity. We actually don't need our chloride ions in this problem. Okay, now let's write the reaction for the calcium oxalate. It will be the same. Okay, and now there is already like a large of amount calcium 2 plus present in the solution because of the calcium chloride. And the solubility product expression, KSP, our constant, will not change. So it will be the same concentration of calcium 2 plus multiplying the concentration of oxalate ions. Okay, and now the concentrations that I will substitute into this expression will be different because the calcium ion concentration is dominated by the calcium chloride. And since the molar solubility of calcium oxalate will be extremely small, we can safely assume that the contribution of calcium 2 plus ions, the concentration of calcium 2 plus ions from the calcium oxalate will be negligible, and therefore we can take that the concentration of calcium ions in the water, in this solution of calcium chloride, will be just equal to 0.100 molarity. And now doing like the same as before, let our X be the solubility of the calcium chloride in this solution. And every mole of, let me do this. So every mole of calcium chloride that will be dissolved in the water will produce 1 mole of oxalate ion. So the concentration of oxalate ion will be just equal to X. 2 minus. Okay, and now we will just substitute these values into our KSP expression. So KSP will be equal to 0.100 multiplying by the X. So, and here our X will be just equal to KSP over 0.100. And this is equal to 0.7 times 10 to the power of negative 8 molarity. So this value is much smaller than the solubility in pure water because the higher concentration of calcium ions will give us the less dissolution of calcium oxalate. And therefore, the molar solubility of calcium oxalate in 0.100 molarity of calcium chloride will be just equal to 2.7 times 10 to the power of negative 8. But now I want to explain one important detail. So in our quick solution, we assume that our concentration of calcium 2 plus was equal to just 0.100 molarity, right? Because from the calcium chloride, and we ignored the extra calcium ions that might be dissolved from the calcium oxalate. So to be completely rigorous, I'm going to prove this, that the concentration of calcium 2 plus ions from the oxalate ions are negligible. So in our 100 molarity of calcium chloride, the initial concentration of calcium 2 plus was equal to 0.100, right? And now let's write the reaction. So calcium 2 plus, the calcium oxalate will be dissolved. Calcium 2 plus, CO2O4 2 minus. So if we had like some X moles per liter of calcium oxalate, then the concentration of calcium 2 plus will be just equal to 0.100 plus X, and the concentration of C2O4 2 minus will be just equal to X. Okay, and now we will put these values into our expression, KSP expression. So 0.100 plus X multiplying by X. And this is quadratic equation. So 2.7 times 10 to the power of negative 9 will be equal to 100x plus x. So x squared plus 0.100 x minus 2.7 times 10 to the power of negative 9, which is equal to 0. So, and if we're gonna solve this, our x will be equal to 2.7 times 10 to the power of negative 8 molarity. And it's like the same as before. We get exactly solubility as before, right? Yeah, right here. Okay, and now if we will compare that to the calcium concentration from the calcium fluoride, which is 0.100 molarity. So this number is really small. It's extremely small. So now it's absolutely valid to approximate that the concentration of calcium 2 plus is equal to just 100 molarity. So if you like, if you wanna like add this number, I mean you can, but you'll get that the concentration of calcium 2 plus will be just equal to 0.1 0 0 0 0 0 0 27. So yeah, we don't need to write this number, right? We can assume that the concentration of calcium 2 plus just equal to 0.100 molarity, and that's it.